integers, which, yes, I'll show you the symbol.
Whole numbers is just natural numbers with zero included, right?
That's right. The integers, now you can pick up your -1, -2, and so this list goes both directions forever, all right? It also includes 0. And the notation for this is a double struct z. Then you have, so what we're doing is we're building more and more numbers, right? And this is actually the way it started when, well, if you believe that humans evolved into a thinking, species, that we didn't just plop down here by something that we had all this knowledge to begin with, right? Like we had to develop it. If you believe that, then the natural numbers were the ones that we first started with. I have 1 sheep, you have 1 bale of hay, I'll give you my sheep for your bale of hay. Like the numbers were used for trade. The number 0 actually was not used for a long time. The number 0 was a huge accomplishment. It was a huge leap forward. The concept of nothing, right? Because I'd never go to you with 0 sheep and try and trade 0 sheep for anything. So 0 came after the natural numbers, and then they got into, okay, how about negative numbers, right? So you have these negative numbers, so now that's the integers. Then we built upon that. And the next thing was called the rational numbers.
I imagine some people got called stupid and stuff for thinking that negative numbers would ever become a thing.
Well, perhaps. Okay, what's the notation for this? Double struct Q, capital Q. It's double struct Q. That like that, I guess.
But that's a line and then
I understand. Okay, it's a double struct Q. All right.
Just
go with it. All right.
This is how it is.
All right. So now, what are these? Fractions. So what it is, what a rational number is this. It's any fraction n divided by m, where m, of course, cannot be 0. Because then you have division by 0. And n and m are from double struct z. So that means take all the numbers in here, okay? All the numbers in here, and make fractions out of them. So like you could take 1 divided by 2, right? You take 1 divided by 3, 1 divided by 4, 1 divided by 5. You could take 2 divided by 1, 2 divided by 2, 2 divided by 3, 2 divided by 4, 2, right? Every possible combination of all of these numbers divided by themselves. That's all fractions, except you can't divide by 0. Yes?
Like pi, for example, would not be a rational number?
Let me keep going. Okay? So y'all with me on this? So this set's building further and further, right? Is every natural number an integer?
Yes.
Every one of these lives in here, right? Does every one of these live in here?
Yes.
Yes? Look at the number 2. 2 is 2 over 1. Are both of those numbers from here? Yes. So all these numbers right here belong to this group, because I can just use 1 on the bottom and just go through the whole list on top. Make sense? Okay, so the question became for a long time, is this enough? Like, is this everything? Are these all the numbers that we need to do everything we need to do? And then we had a problem like this.
22 divided by 7.
I'll go a little more simple. Where you have a right triangle, this is 1 and that's 1. And you want to know the length of the hypotenuse. Well, Pythagorean theorem, right, says that this side plus this side must equal this side, right? So let's call this C. If we're using a squared plus b squared must be equal to c squared, then we know that 1 squared plus 1 squared must equal c squared. 1 squared, that's 2 must equal c squared, which means that the square root of 2 must be c. And the question was, is there a fraction, right? Is there a fraction somewhere in here where I take one of these and divide it by one of those, something in here that would give me root 2? And the answer is no. There is no way that you can ever make that number from a fraction. It's impossible. It's one of the first things I ever had to prove when I was in a, you take these classes, if you're a math major, you take a class called Foundations of Math, Foundations of Mathematics, which is where you start proving things, and that's one of the first things that they make you have to prove is that this is not, can't be a fraction.
Is that class interesting?
I guess it just depends on if you like this stuff. It's hard. It's hard because it's logic. There's a lot of logic in it.
Math, I have to take every class. So
You do have to take that class?
if I want to minor in it.
Yeah, I mean, I think it's a good class. It kind of opens your eyes up to, you know, some stuff. But
'Cause I
okay,
still
so
have to take 2 classes of minor math.
this number is not a fraction, and there are a lot of numbers that are like this. Pi is another example, and there's another what? E? Okay, so we're going to talk about E later, but we may as well talk about it now. E is approximately 2.718. Pi is approximately 3.14. Now, that little squiggly equals is actually a math symbol. I'm not like making that up. It means approximately, okay? It's like a drunk equals, like kind of, it's like close to this, right? It's kind of that. So that's what that is, right? These numbers, the property that these have is that if you were to continue to write these out, it would never stop and it would never repeat. So like if you've ever seen something like 1/3 is equal to 0.333, that repeats itself, doesn't it? Yeah. This is a rational number because it repeats. It goes forever, but it repeats. So we call these irrational numbers. These are irrational. And I don't know why, but I can't remember if there is a symbol for the irrational numbers.
Double strung I.
No.
Google it.
I'll look into that. I don't think that there is one that's commonly used. Go ahead. You have my permission to Google it.
Google that mother. First one to Google.
All right. Okay, so look, if you were now to put all the irrationals into a big old pot, there they are, and you put all the rationals together, which are all the fractions, and you dump them all into this pot. Okay, throw them all in there together. Those are the real numbers. Your real numbers contain all of those. All right? And the real numbers have a very important property that they create what's called a field. And the field is the structure of our number system. And being a field is a very, very strong, there's some very strong conditions to be a field. It's beyond the scope of this class, but I just want you to understand, like, if you were to study mathematics, you get very deep into the structure of things and how things behave. So, okay, why am I telling you all this? Because
You thought it would be funny.
Because this whole thing that we've been doing about breaking this thing down, right, is called the rational zero test. And it works only when your x-intercepts are rational numbers. That's the only time the test will ever work. Notice that every single x-intercept that we got was like 2, right? -5. We did have what, 5 halves on the last one? 5 halves is a rational number, right? And it worked. But if I give you something that does not have rational zeros, the test will fail. And I'm going to give you an example right now, just to show you that the test doesn't always work. So how about if we did f of x equals x squared minus x plus 7. Now I'm giving you a quadratic, okay? I'm giving you a quadratic, well, let me make this number a little more interesting. Giving you a quadratic because it'll be easy for us to work with. So you sit there and you say, I'm trying to factor that, I can't figure it out, right? So you go and you make your list. What's the good thing about your list?
1, 2, 4, 8.
it's because you have a 1 up there, right? You're just going to have a short list. It's going to be 1, 2, 4, and 8. And then you go through with your synthetic division, right? And it's 1, -1, 8. Maybe I should have made it a shorter list. I don't know. Because do you really feel like going through all 8 possibilities?
Yeah.
No, you don't. I don't. Look, if you try all 8, none of them are going to work.
All vote. Everyone that voted said yes to this.
Then why
None
don't
of-
you change back to 7?
that wouldn't work either.
I know.
Oh, you want me to change it to 7 just so you can see?
For the list.
Okay. Because all it would be is this, right?
Yeah.
Okay, so let me try 1 here. I would get 0, 1, 1, 0. Ooh, 0, nope, doesn't work, right? Let me try -1. 1, -1, -2, 2, nope. 7, 1, 7, nope. You'll see this? -7, 1, negative, no, right? So does that mean it doesn't factor?
Yes. Voted.
No, it doesn't. It just means that all it means is that
Quadratic form.
the intercepts, the x-intercepts, could possibly be irrational.
Oh.
So where you cross through could be something other than a fraction. So as great as this strategy is, its limitation is that it will not factor something that doesn't factor over rational numbers. If it factors over rational numbers, then we're in business. I'll give you another quick example of this.
Are you going to give us one of those on here?
No, I wouldn't try and confuse you, no. But like, let's take a look at x squared plus 4, right? Right? If we try and find the x-intercepts of that, we won't have any. Because we know that's a parabola that's been moved up 1, right? Well, you know what? Let's do this. This will be more interesting. Does that have x-intercepts?
Yeah.
Right? Okay. So that should have x-intercepts. If I set up synthetic division on this, what goes in here?
1, 0,
1, 0, -2. What's my list?
1 and 2.
1 and 2. You all following that? Try
Job looks easy.
1, 1, 1, 1. Okay, that doesn't work, right? -1, 1, -1, -1, 1 doesn't work. 2, 2, 2, 4 doesn't work. -2, 4 doesn't work. See, it failed, but we have x-intercepts. So how would we get them? We would use a quadratic formula. But what if your polynomial is every x-intercept is an irrational number? You're screwed. That's exactly what I was going to say. You are screwed. But we would never give you something like that. Okay? I just want you to understand although this is very powerful, it's limited. Yes.
Would we have to deal with that in like Cal 1 or Cal 2 then?
Well, what you do in a calculus class, what you realize is that there's other ways for us to find x-intercepts. It's called Newton's method, and it uses calculus to do it.
Like Sir Isaac Newton?
Yes. Who's the father of calculus. So we use other methods to approximate zeros, and that's exactly what your calculator does when you ask it to solve. Same thing that Wolfram Alpha does when you try and solve an equation. It uses some form of Newton's method. So, bye. Have a good day. Are we almost? Okay, we're not out of time. All right, so where do we go from here? We good? We happy?
We go to the time machine to go assassinate Isaac Newton so we don't have to
Easy, easy. I take that personal.
Yeah, but then you wouldn't have a lot of things. You wouldn't have this taste. You wouldn't have microwaves.
Yeah, but who uses microwaves nowadays?
No hot pockets.
I don't know your microwave oven.
No hot pockets.
No cell phones. No.
I'm debating right now whether or not I should go back and take care of quadratic inequalities and polynomial inequalities. Why don't we do that? Why don't we take care of 5, 4? I think we can knock 5, 4 out pretty quick. I'm sure.
We ask a lot of questions.
It's all right.
Realized.
No, it's good. This is what math should be about. It should be dialogue that's happening, not just information coming out. There should be some back and forth here. All right. I want to start this by first making sure we're all comfortable with what an inequality is. An inequality is not an equal sign, right? It's the symbol that they use. It's that, or it's this, or it's this, or it's this, right? So let's make sure we understand what each of those means. This means x is
greater than y.
larger or greater than? Either one, larger than or greater than. So on a number line, this means that x must be to the right of y. That's what it means. If we flip it the other way around, these flip, right? If we use this symbol instead, I'll put it right here, then x is greater than or equal to. So that would mean here's y, here's x. That would work, right? That would satisfy that? That would be okay? But I could also do this. That they're the same point. They're the same number. See, I couldn't do that here, right? I couldn't put the x on top of the y. All right, so that's what an inequality is. Equality and inequality is different, right? So let's now look at something that we should all be comfortable with, which is what's called a linear inequality. Linear inequalities would look like this. I'll give you a specific example. X plus 4 less than negative 5. That's an inequality. It's linear because x is being raised to the first power. Yeah? And so to solve a linear inequality, all you have to do is isolate x. So let's subtract 4 on both sides. We get x is less than negative 9. And so if I were to try and draw a picture of that, here's negative 9. It's all the points less than, right? So we're looking at all of this out here forever, right? And then we could do that in an interval. It'd be negative infinity to negative 9, parentheses on both. So we're familiar with this? Okay. What's the one thing we have to be careful with linear inequalities? Like, let's say I have negative 3x is bigger than or equal to 9. If I'm going to solve that one. Yeah, if I come through here and divide by negative 3 on both sides, with inequalities, if you multiply or divide by a negative, this has to flip. So you go and you make this x, you make this negative 3, but that has to flip. That's what happens anytime you divide or multiply an inequality by a negative number. Do y'all remember ever seeing that before? Okay. So this would be negative 3. Anything to the left of it, right? Or it could be negative 3. So the interval would be negative infinity all the way up to 3 with a bracket. We're good or not? Okay. That's not what we're studying now. What we're looking at now are polynomial inequalities. So I'm gonna begin by giving you one and seeing how you would solve it. You ready? Here you go. X squared plus 3x minus 4 less than or equal to 0. So what I'll ask you first is this a polynomial inequality? Okay, you have an inequality, right? Is this a polynomial?
Yes.
Yes. So this is a polynomial inequality. How do we solve it?
Should we factor it?
Okay, you want to factor it? Let's go ahead. Let's factor it. Let's see what happens. X plus 4, x minus 1, less than or equal to 0. Is that what you want me to do?
I guess.
Yes? I'm just going to follow you down this road and let's see what happens.
Let's follow down the rabbit trail. I don't like how we're going.
Now what?
Separately, we solve for x.
You want to do separate these each? So you want to go x plus 4 less than or equal to 0, and then the other one, x minus 1 less than or equal to 0.
Yeah.
Does that seem logical that that's what you would do?
Yes, because you can divide
Because
either
it's
side.
kinda like if
You can divide 0 by either side.
Hold on. I'm asking the question, does it seem logical?
Yes.
It's wrong, but does it seem logical?
Seems logical.
Okay, because I agree with you. Someone's going to do this on the test. I don't want you to be the person who does it. Okay, because I'll take off major points if you do it this way. I hate to show people the wrong way. But this happens so many times that I have to show you what's wrong with this, all right? Let's just convince ourselves this isn't going to work. Here, how about you subtract 4 on both sides? Negative 4 here. Over here, you add 1 to both sides. Okay, good?
All that gives
All right, let's take a look at what that is on a number line. X must be less than or equal to negative 4, which would be negative 4 less than or equal is everything to the left.
Yep.
Okay.
And then,
And this one is x is less than or equal to 1, right? Which would be everything this way, like this, forever. Well, I don't know, is it?
No.
It's the same list with more
It's the
numbers.
same
added.
list as when we-
Yeah, it's the same thing, but we added a little bit more to it. So according to this, right, anything in here should work, right? So let's test a point. Let's just test something. How about in here? How about 0? 0's in there, right? Let's see if 0 satisfies the original problem. 0 here, 0 here. Negative 4 is less than 0. Would that work?
Yes.
Yeah.
Negative 4 is less than 0. Check. Okay, try something here.
Negative 5.
Negative 5. Okay, what's negative 5 squared? 25 plus, what's 3 times negative 5? Negative 15. Okay, minus 4. Is that less than or equal to 0?
No.
So that's 10, right?
6.
10 minus 4 is 6. 6 is not less than, something went wrong. Right? Something went wrong. Here's why this doesn't work. Let me see if this makes sense to you. For something to be less than 0, it has to be negative, doesn't it? Or equal to 0, right? It has to be negative to be less. If I take two numbers and multiply them together, if they're both positive, your answer is what? Positive. If they're both negative, your answer's positive. But if they're different signs, it's negative. That's what's causing the problem. It's the property that two negatives multiply to be positive. And so what's happening here is that when you're getting one answer, right, less than this, you're getting a negative number, right? And then over here, right, over here, you could get another negative number, right? If I pick a number in here, I could get another two negatives together that multiply, and there's no way that they're going to be bigger than 0 because it's going to be positive. So how in the world are we going to do this? Do you understand the problem? Like, you can't do this. This is a big no-no on solving polynomial inequalities. So what's the workaround? There's a nice quick workaround for it, all right? Check this out. It's so awesome. Nope, here's what you do. You first take the polynomial inequality, you convert it to an equation. Okay, let's convert it to an equation. So let's make it an equals, even though that's not what's being asked, right? That's not what's being asked, but let's go ahead and look at that, all right? Now for this, could you solve this equation? Yes, that you could come in here and do this. Agreed? And you get your two answers, and they would be -4 and 1.
That's it, the points.
And those are points, right? Now, my question to you is, do I want to include these points or not? Yes or no?
Yes.
Yes, why?
What is it equal to?
Because if I plug these points in, I'm going to get 0, right? And this right here had the less than the bar underneath, and that means we are allowed to be 0. So these two numbers will actually satisfy that. The question remains whether or not anything over here does, anything in between these does, or anything over here. So there are two approaches to this. One approach is just check some numbers. You want to just check some numbers we could test? It's one approach,
Well, if we're given multiple.
right?
What's the other one?
The other approach is if I asked you to graph that, do you know what it looks like?
Not right now. but
Yes, you do.
Yeah.
Look at that. You know what that looks like?
Oh, yeah.
What does it look like?
It does.
It's a U that goes up, and it has two x-intercepts, doesn't it? So it looks like this, right? Yes, and what you want to know is when this is what? Less than 0. Can you tell me when that's less than 0? Can you tell me when that graph is below the x-axis?
Yes.
Right here. That's the solution. You understand? This part dipping below is the part that corresponds to the part that's negative. Understand that? Yes.
So if we do that, like, and it's a different equation, and for whatever reason off the top of our heads we don't remember what that graph looks like, we would just look in between each 2 points and at the far sides pick 1 point.
Yeah.
from each.
So what I would do here is I would test -5. We did that earlier, didn't we? It did not work, so I would cross out that region. We picked 0 earlier, didn't we? And it worked. I would check that region. I would pick one more test point, 2. I would check it in here, and let's just check it real quick. 2 squared, 4 plus 6 minus 4 less than 0? No, that doesn't work, so this wouldn't work. So it would be these two endpoints and everything in between. But if you know what it looks like, it's sure a lot faster, isn't it? Yes?
So you would write that in interval notation?
So your answer would be an interval. Yes, your answer would be to this. Your solution would be the interval, bracket, -4, 4. There you go. That's your solution set. 1, sorry.
What?
1.
Magic number.
Magic.
Curves back down for whatever reason.
Okay, you understand the idea here? All right, so let's take a look at one of these here. Let's look at that first one. X plus 4 squared, x minus 3, x plus 8 greater than 0. Is this a polynomial inequality? Yes, because the left side of that, if you multiplied it out, would be a polynomial, wouldn't it? The way to solve these, I said, was to convert it to an equation, right? So let's convert this to an equation. X plus 4 squared, x minus 3, x plus 8 equals 0. And that's actually really nice now, isn't it? You can just set each of those equal to 0. What would we get? -4, 3, and -8, right? So right now what I know is this. -8, -4, and 3 are the points that the values that would actually make this thing equal 0, right? Do I want to equal 0? No, I want to be greater than 0. So what I'm going to do is I'm going to mark these, but I'm going to leave them open because I do not want those to be involved in my answer, right? But they do create some regions for me to look into. So at this point right now, I could just start testing, right? Take a point over here, test, test, test. Or if you know what it looks like, you can do it that way. So do we know what this looks like? This is -4, and it does what here? Touches, and here it crosses, and here it crosses. What's the one other piece of information I need? How does it open? So we come back over here. This behaves like what? X squared. Then this behaves like x. This behaves like x. Put those together. X to the 4th. I go up, up, don't I? So what I can tell you here is that the left side goes up. The right side goes up. I cross through at -8. I what? Touch. come back down, and cross through. Understand what I'm doing? And the question is, when is this thing positive? Where is it positive?
So
Negative infinity.
negative infinity to
Right? Above the x-axis?
parentheses.
And then
Over here.
3
Right?
infinity.
And that's it.
With parentheses on all ends.
So the solution to this is negative infinity to negative 8, parenthesis, union, 3 to infinity, parenthesis. That's the solution set for that inequality. What do y'all think?
A lot easier than I thought.
Yeah, not so bad?
It was an easy one to grab because it was,
Yeah, I gave it to you that way, right?
but typically do we do the elimination process or graph? What would be easier for what we're gonna have?
It really depends on you and what you're comfortable with. You know, if it looks like you can fire that out quickly and go off that, the test points sometimes is faster. So why don't we do this? I'm going to give you as a take-home assignment. And this, we need some quiz grades, right? So why don't we make B, C, and D take-home quiz to be turned in next class? Keep those. I'm not going to collect that one.
Oh, I thought you
As,
said you were broken.
yeah. Did I say I was going to collect it?
Yes.
Bring them both next time. How about that? That sound like a good deal? I'll give you 2 grades for them.
Sign in.
Yeah, let's do a sign-in. I've got time for it. We haven't done this in a while, have we? Let's see, today's the 25th. All right. Do you all prefer to sign as you leave? Yes? Okay. So I'll just put it right here, initial in the column that's empty. Everybody have a great weekend. I think what I'm going to do is, those are the 3 problems I want you to try. I might email y'all a couple of more problems out of the book for you to just look at for sketching polynomials, just for more practice. All right? So just keep an eye on your email in the next day or 2.